These notes are for the energy unit, and they're for worksheet number 1, the front page, which is problems 1 through 5. So measuring heat transfer. There's an equation for measuring heat transfer, and I call it Q SMAT. Q, S, M, delta T. The delta looks like an A, so I call it SMAT. Q is the amount of heat transferred in calories or joules. And you would think that Q would be H, but H has been used for enthalpy, so Q means heat transferred. M, I'm doing this letter right there. M is mass of the substance in grams. Delta T is the change in temperature in degrees Celsius. It's usually the final temperature minus the initial temperature. And the S is specific heat capacity in calories per grams degrees Celsius. It also could be in joules, and you just have to look at a table for that, or it's given to you in the problem. And you can use this equation to determine the amount of heat transferred, the specific heat of a substance, the mass of a substance, or a change in temperature. Specific heat capacity refers to the amount of heat needed to raise the temperature of a substance by 1 degree Celsius. So every substance has a specific heat capacity. The specific heat is different for different states of matter, meaning solid, liquid, or gas. There's an example below in units of calories per gram degrees Celsius. So aluminum, solid aluminum has a 0.2 specific heat capacity. Liquid water is 1. Solid copper is 0.09. Solid iron is 0.11. Nitrogen gas 0.24. Hydrogen gas 3.34. So here's a chart of specific heats. I believe that one of these numbers up here is not correct. What does specific heat mean? The greater the specific heat capacity of a substance, the less its temperature will rise when it absorbs a given amount of energy. A low specific heat, meaning a smaller number, means a substance will easily change temperature. Going back to the first one, a higher temperature means the temperature doesn't change as quickly and needs a lot more heat put into it or pulled out of it. So water, liquid water has a really high specific heat. Liquid water can take an input of a lot of heat or the output of heat going out before it changes either into a gas or into a solid, which is like ice. So here's a calculation. How many calories of energy does it take to heat a 75 milliliter sample of water from 25 degrees Celsius to 38 degrees Celsius? We're going to use Q SMAT. And remember that 1 gram of water is 1 milliliter of water, and this is only true for water. So we could say the mass is 75 grams. The specific heat from a chart is 1 calorie per gram degrees Celsius. The temperature is the final minus the initial. So we have the final, which is 38 degrees, minus 25 degrees is 13 degrees. Now we're going to plug and chug. Put the specific heat here with the units, the mass here with the units, the temperature here with the units, and make sure they all cross cancel and leave us with calories, which is a unit of energy. 975 calories of heat is transferred into the water. So calculations with mixtures of water. So here's a chart. So if you did trial 1, you had 100 grams in one beaker and 100 grams in another beaker. And the first beaker was at 20 degrees Celsius, and the other beaker is at 80 degrees Celsius. When you mixed it, the final temperature would be 50 degrees. So both masses are the same, so the temperature is going to meet in the middle between 80 and 20. So you go 20 plus 80 is 100, divided by 2, because there's 2 samples, is 50 degrees. This next trial has 100 grams in this beaker, 100 grams in that beaker, so the mass is the same again. So the final temperature will be in the middle of 20 degrees and 70 degrees. So 70 plus 20 is 90, and half of 90, since there's 2 of them, is 45 degrees. It gets changed up, though, a little bit with the trial 3 and trial 4 because the masses are not the same. You can look at trial 3 and say, aha, it arrives at 65 degrees. That makes sense that the final temperature is closer to 80 degrees because there's more mass in that second beaker as opposed to this one. And in trial 4, you could say there's 200 grams at 20 degrees Celsius and 100 grams at 80 degrees Celsius. The final temperature should probably be closer to the 20 degrees than the 80 degrees. And it is. So how do you figure this out without actually just taking a wild guess? So this is an example that is not on the worksheet. So if you had 300 milliliters of water at 60 degrees Celsius and 100 milliliters of water at 20 degrees Celsius, and you mix them, what's the final temperature? And the final temperature is going to be the amount of heat transferred. So first you must find the final temperature. And there's two methods. You could do a weighted average method, or you could do heat lost equals heat gained method. And the heat lost equals heat gained method always works. The weighted average method only works if both substances mixed are the same type of substance, like water and water. So here we go, the weighted average. You do 300 grams, that was at 60 degrees Celsius, multiply them, add it to the 100 grams, it's at 20 degrees Celsius, and you divide it by the total mass, which is 100 plus 300 is 400, and you get 50 degrees. This again works only if it's water mixed in water, or steel mixed in steel, corn syrup and corn syrup. The next method we're going to show you, I'm going to show you, is heat lost equals heat gained. This works for all substances. So if the heat lost, which is Sm delta T, and the heat gained is Sm delta T, using the transitive property in math, you can put the two SMATs equal to each other. So you could have the SMAT of the one that loses heat equals the SMAT of the one that gains heat. The one that loses heat is usually the one that's temperature gets smaller or goes down, and the SMAT of the one that gains is the one where the temperature tends to go up. So in this case, it's the specific heat in both of these is the same. It's 1 calorie per gram degree Celsius. This one had 300 grams, that one had 100 grams. And here we go, 60 degrees minus X, which is the final temperature that we don't know of. And here it's X minus 20 degrees Celsius, and X is the final temperature. And here it's minus X, so you end up with a positive number. And here I know X is going to be bigger than 20, and it's also so you get a number bigger than a positive number, sorry. And I know you can do all the algebra. You do multiplication, some division, some subtraction, and eventually you solve for X. And when you solve for X, you get 50 degrees Celsius. So the last step of mixing water, how much heat was transferred during the mixing of the water? So we use QSMAT. The heat loss should be negative because you lost heat. The heat gain should be positive. So the heat lost was negative 300 calories, but the heat gained was positive 300 calories. It's just the opposite. So heat lost equals heat gained. Why do things have different heat capacities? Why do you need more energy to raise the temperature of water compared to methanol, or copper or aluminum? Assume same mass of each. So two contributors, molar mass and bonding. And in bonding, there's the type of molecule, polar or nonpolar, and the size of the compound can lead to different opportunities for bonding. So molar mass affects heat capacity. If you had 1 gram of copper and 1 gram of aluminum, the aluminum heats more quickly because it has a smaller molar mass. There are less atoms of aluminum, 27 grams per mole from the periodic table, in 1 gram to heat than in 1 gram of copper, which is 64 grams per mole, periodic table again, due to the difference in molar mass. It makes sense that more energy is required to cause a larger number of atoms to move faster in the substance with more atoms. Bonding affecting heat capacity. Substances with polar bonds, ionic in nature or polar covalent, tend to have higher heat capacities than nonpolar substances. These substances have more intermolecular attraction to one another. That means one molecule is more attracted to another. And the more attraction you get between molecules, the more energy it will take to overcome the attraction. For example, in water, the H's are attracted to the O's and vice versa. It's called hydrogen bonding. It's actually a pretty strong type of bond. It's not a true bond. And it takes a lot of energy to separate the attraction between the H's and the O's. The size of a molecule also impacts its heat capacity. Larger molecules can have a variety of internal vibrational motions. It takes a lot more energy to overcome the attractions created within a large molecule due to these vibrations. Hydrogen bonding is a very strong attraction between hydrogen and other atoms, specifically nitrogen, oxygen, and fluorine. If a molecule exhibits hydrogen bonding, it takes a lot more energy to overcome this attraction. Water is the perfect example of hydrogen bonding. That is the end of our notes for the front of worksheet 1, problems 1 through 5.